So for the second bulk of this chapter, we're going to talk about titrations. And let's just recall what titrations are. First, when we were looking at chapter 6, we looked at aqueous solution reactions. The first one that we learned about was precipitation reactions. And from there, we have figured out that through this technique called gravimetric analysis, wherein a precipitate crashes out of solution, you can determine the identity of an unknown ionic compound. We'll look again at gravimetric analysis in chapters 15.1 and 15.2. But another means of analysis before that we have established is volumetric analysis by titration. Now, unlike gravimetric analysis, in titrimetry, you do not see the end of the reaction with your naked eye, meaning no precipitate crashes out of solution. But instead, you have the use of what's called an indicator to basically indicate, as the name implies, when you are close, not at, but close to the point at which the acid fully neutralizes the base. So titration basically is for neutralization reactions, an acid and a base, and the equivalence point is the point at which the acid fully neutralizes the base. Okay. Now, there are some terminologies that I want you to know. The titrant basically is something that is being added to the unknown, the titrand or the analyte. Let's call it analyte. Titrand is an archaic word. The concentration of the titrant, remember we have discussed this too in chapter 6, is determined by yet another titration using standardization. In standardization, it's actually easy to determine the number of moles of these primary standards. Okay. Now, we cannot really see the equivalence point with our naked eye, but using these weak acids called indicators, we can actually guesstimate where they are at. The point at which the pH changes the color of the indicator is the endpoint. So the indicator actually should be chosen such that it estimates the equivalence point. We're going to discuss in another video how to properly pick an indicator for an acid-base titration. But for now, let us look at the different kinds of titration. Okay? And we will actually take a deeper dive into titration, unlike what we did in chapter 6, wherein we were just doing stoichiometry. Here, we will actually be looking at titration curves. Okay? They're basically a graph of the pH as a function of the volume of the added titrant. This is actually pH setup, even though this meme is funny. This is where you put the titrant or the, again, solution which you know the exact molarity of. Here is where you put the analyte, okay, so in this Erlenmeyer flask, okay. And from the titration curve, what people are actually doing is, as they are adding titrant during titration, using a pH probe or a pH meter, people actually measure the pH of the solution and graph it as a function of how much volume of titrant you're adding to the titration mixture. Okay, we'll be looking at 3 different cases. Strong acid versus strong base. Weak acid with with strong base, and weak base with strong acid. Okay, let's look at the case of a strong acid being titrated with a strong base. So when I say strong acid with strong base, if you consider a titrimetry setup, okay, with a burette, and you have your analyte in an Erlenmeyer flask. So the titrant, which is in the burette, should be the strong base. Okay, so that's the titrant. And then here in the Erlenmeyer flask should be the strong acid, the analyte. Okay. Now this graph shows the pH of a solution of hydrochloric acid as a function of volume of the titrant strong base added. Here the titrant is sodium hydroxide, and the strong acid, which is the analyte, the one that you're trying to determine, I guess for this, the concentration of, or at least you're monitoring the pH of, is HCl. Okay? There are four regions of interest that we would like to look at. First will be the initial pH. At the initial pH, when basically no sodium hydroxide is being added, notice that the pH is very low. Okay? And that's just because the only active species you have here will be the H plus from HCl. So remember that HCl is strong acid, so it actually breaks up into H plus and Cl minus ions. Okay, chloride ions do not have any acidic or basic properties, but H plus is very acidic. Okay, so this pH is actually going to be based on the concentration of hydrochloric acid initially. Now, as you add sodium hydroxide into the Erlenmeyer flask to react it with HCl, so that we see an increase in pH as you add more and more sodium hydroxide. Okay. However, at this pink region, which is the second region of interest between the initial pH and the equivalence point, the sodium hydroxide is the limiting reagent, whereas HCl is in excess. That's why the pH values are still acidic. Now, at a point wherein the number of moles of sodium hydroxide is equal to the number of moles of hydrochloric acid, they have fully consumed each other. Okay, what is left in the solution will just be water and sodium chloride. Okay, at this point, that's the equivalence point. Okay, and note that from chapter 13, we have mentioned that the product of a strong acid plus a strong base should be a neutral salt. Okay, so that is why the equivalence point of a strong acid, strong base titration should be equal to 7. Okay, now beyond the equivalence point, we have already fully consumed hydrochloric acid, and now this time there is an excess of hydroxide ions. So the pH from this equivalence point, notice that it actually shoots up quickly to basic values. So one thing that you should note about this titration curve between a strong acid and a strong base is notice how steep this point at the this region near the equivalence point is. So there is actually a drastic change of pH at around this volume. So let's just say that is around maybe 24.9 ml. Okay, because the equivalence point here is at 25 ml. Okay, notice how there is a dramatic spike in pH, and then there's also a dramatic change once you add another 0.1 ml. So this one's at around 25.1 ml. Okay, so this is characteristic of strong acid, strong base titration. Now, what if you have it the other way around? What if hydrochloric acid is in the burette and sodium hydroxide is in the Erlenmeyer flask? So that's a very rare case, not really rare, I'd say. That is unusual. Most of the times you have sodium hydroxide in the burette, but for some cases it's actually used, in which a strong acid is the titrant. But the titration curve still has some similar behaviors. As you can see, the only difference is we just start at a pH which is basic. Okay, but at this point we have an excess of OH ions. Okay, excess of OH. And then to the right of the equivalence point, we now have an excess of acids, or H3O+. Okay, but the pH still is at 7, because again, this is a strong acid and a strong base. It will produce a neutral salt. Alright, let us look at this problem, 14.57. I'm sorry if this video is going to be long, But what I want to do next will be to calculate the pH of um, this solution in the Erlenmeyer flask as we are actually adding the sodium hydroxide. We want to see again um, how the pH is actually changing as a function of volume of sodium hydroxide added. Okay, so in this case, again, if you have a titration setup, then you have KOH in the burette, okay? And then in your Erlenmeyer flask, you have perchloric acid, okay? And we want to calculate letter A, what if we do not add any KOH from the burette yet? So if that's the case, then keep in mind that the solution that we're going to measure the pH will be perchloric acid. Remember that perchloric acid is a strong acid, okay? And therefore, if the concentration given here by perchloric acid is 0.200 molar, okay? Concentration of perchloric acid is 0.200 molar. And remember that perchloric acid, being a strong acid, readily breaks up into H plus and Cl O4 minus ions, perchlorate ions. So this one should be the amount of H plus you have in solution. Okay, now that you know that the amount of protons in solution, then the pH just becomes negative log of that value, which is 0.200 molar. Okay, and this will just give you 0.699. Okay, that's the pH of the solution before you add anything. Okay, let's work on the next one. What if you add 10 ml of potassium hydroxide to the burette, or to the Erlenmeyer flask rather? Now, when we are working with that problem, I'd like to stay on this slide first. We, of course, want to write a balanced equation first. So the balanced equation for this reaction will be, you have perchloric acid plus potassium hydroxide going to produce water, okay, plus potassium perchlorate. Okay, now remember that these products were derived just from the fact that a neutralization reaction is a double displacement reaction. But what we want to actually use, and that's a pro tip, is the net ionic equation. So instead of writing this equation, let us actually consider, when we write ICF tables for letter B, the net ionic equation instead. Now, remember that this is strong electrolyte, also a strong electrolyte. This is liquid, and then perchlorate, potassium perchlorate will break up into ions as well as a strong electrolyte in solution. So the net ionic equation that we're going to use is actually H plus, okay, plus OH minus going to H2O. Now, why am I using the net ionic equation instead of this one on top, which is the molecular equation? So right now, the relationship between perchloric acid and potassium hydroxide, this one is to 1, meaning 1 mole of perchloric acid will react with 1 mole of potassium hydroxide. But if you have, let's say for example, a dibasic strong base, for lack of a better word, I guess, dibasic strong base, let's stick with that. If you have a strong base with 2 hydroxide ions, remember that whatever the concentration is of that base, let's say barium hydroxide, if you want to determine the concentration of hydroxide ions, that should be 2 times the concentration of barium hydroxide. Okay, and it actually makes calculations with ICF tables difficult. So let's stick again with just the net ionic equation. And that's what we're going to use with this video and the next 2 videos about titration. Okay, so for letter B, we have a reaction. Okay, we're adding 10.00 ml of KOH. Okay, so basically the H plus, again from perchloric acid, will react with the hydroxide, from potassium hydroxide, and they will form water. Okay? Since this is a reaction, we want to write an ICF table. Okay? And let's just use millimoles because we're given volumes in milliliter and molarity. Okay? So I, and then C, and then F. Okay, I'll be writing this a lot. So let's determine how much millimoles of H plus we have. So we're given a volume of 40.0 ml. Okay, and then the concentration is 0.200 molar. Okay, if you multiply that together, that's 8.00 millimole. Okay, and then we have 10.00 ml of potassium hydroxide. Okay, or OH basically, and 0.100 molar concentration of OH. Okay, if you multiply them together, that will be 1.00 moles or millimoles. Okay, so the change here should be the limiting reagent is OH. So this should be minus 1.0. It will be fully consumed basically. Minus 1.0. And then this is plus 1. But you don't really care about water. Okay. So in the end, you will have 7 millimoles of H plus left. You have no leftover OH. And water, again, you don't really care. Okay. So here, you can calculate the concentration of H plus. Okay, you have the millimoles of H plus. So from that millimoles, divide that with the total volume. Okay, again, total volume. Okay, of the new solution. So that should be 40.0 plus 10.00 ml. Okay, 40 from the acid and 10 from the base. Okay, and when you do the math, that will become 0.140 molar. Okay, and therefore the pH of the solution is negative log of 0.140 molar, which should be 0.854. Notice that the pH of the solution has increased. Okay, by around 0.2. Okay, let's now calculate for letter C. What about after you add 40.00 ml of NaOH? Okay, so let's again write an ice table, the similar ice table that we have written earlier. Okay, so millimoles, H plus, and then OH minus, going to yield H2O. Okay. We already know what the millimoles of H plus is. We've calculated that already. That's 8.00. Okay. For OH, we begin here. We have here rather 40.00 ml times 0.100 molar. Now, one thing that you may ask, why do we actually begin here with 8 millimoles? Didn't we end up earlier before with 7 millimoles? So when working on titration problems, you assume that you're working with each step in the titration, with each volume that you're asked for one by one. Okay, so basically what you're going to put here is I initial for what you originally really begin with. Okay, you're not going to put here the number of millimoles from the previous reaction. But anyway, we haven't computed this one yet. So after doing the math, that should be 4.00 millimoles. Okay, and then water is also 0, or is 0. Okay, and then the change should be hydroxide is still the limiting reagent, so that's minus 4.00, minus 4.00, this is plus 4.00, this is 4.00, 0, and 4.00. So therefore here, the pH of the solution should be again negative log of the hydronium ion concentration, or H plus concentration, which is 4.0 millimoles, divided by again the total volume here, which is 40.0. Notice that this was the original amount, or the initial volume anyway, of H plus to begin with. Well, H plus is in perchloric acid. And plus 40.00 ml. Alright, and that should just give you negative log of 0.0500 molar. Okay, and the pH therefore of the solution should be 1.301. We have 3 decimal places because we have 3 significant figures here. Okay, and then let's go to letter D. Now, what if you have added 80.0 ml of sodium hydroxide in the solution? Okay, again, as I have mentioned earlier, we have to actually start with 8 millimoles of H plus. But let me complete the ICF table first. Okay, so we start with 8.0 millimoles of H plus. Where did I get that value? Again, we have solved that from the very beginning. Okay, oops. And then this one should be 80.00 ml times 0.100 molar. Okay, there should be 0. And this one should be equal to 8.00 as well. Okay, the change should be minus 8.00. Okay, I mean, both of them will be fully consumed by each other. Okay, and we're actually left with no H plus and no OH minus. Okay, but we don't care about water. Now, this just means that this is the equivalence point. Okay, and well, we don't have actually any values here of H plus or OH minus. But since we know that this is a titration between a strong acid and a strong base, the pH should be equal to 7 because this is a neutral salt. Now, these values are 0 just because, remember, the concentration of H plus and OH ions at a pH of 7 is actually equal to 1.0 times 10 to the negative 7. Okay, so it's a very low number. That's why we actually see 0 here. Okay, and then lastly, let us work with the plus 100 0.00 ml of OH. So keep in mind that for E, we're now actually past the equivalence point. Okay, H plus OH minus going to yield water. Okay. All right. So for this one, again, we still begin with 8 molar of H plus. Okay. For OH, we have 100.00 ml times 0.100 molar. Okay, this one will be equal to 10. Okay, and then this one, or 10.0, let's use appropriate number of sigfigs. Then water is 0. Now this time, H plus is the limiting reagent. Okay, because again, we're past the equivalence point, so therefore now we actually have an excess of OH minus in solution, or hydroxide ions in solution. So this is 0, this is 2.0, and then this one is 8.00. Okay, and we have OH. Okay, so we can actually calculate POH based on the hydroxide ion concentration. So the POH of the solution, therefore, should be equal to negative log of 2.0 millimoles divided by the total volume again, which is 40, oops, let's just write that better, 40.0 plus 100.00 ml. Okay, that should just give you negative log of 0.014 molar. Okay, therefore the POH is 1.85, but we are asked for pH, so therefore the pH of the solution is 14 minus 1.85, So that should be equal to 12.15.